how do we figure out the pH if we have two acids, right? So this is what we talked about last time. And so when you have two acids, what you want to do is if they're not close to each other in their Kas, then you just use the biggest one because the other one's going to become negligible. And I'm going to show you this a couple times today, how this works. So for this question, it's determine the pH of a solution, and it's got 0.045 HCl and then 0.15 HF. But remember, HCl is a strong acid, right? So since it's a strong acid, that means that the HF is going to completely, we're going to be able to ignore it because lactate is going to make that HF dissociate even less than it did before. All right, so we talked about the Y last time. So now this problem is actually pretty straightforward. All we do is ignore HF. And so in this question, really all we care about is this. So just negative log of that, because it's a strong acid, we can just ignore the weak acid. And then when we do that, I have to get my calculator out. It's just negative log of that, 1.35. And that's the whole problem. Okay, so if you have a mixture of a strong acid and a weak acid, you can ignore the weak acid. You just have to do the strong acid. Now, there's sometimes when we can't do this with mixtures, but those are usually polyprotic and diprotic acids. And we'll talk about polyprotic or diprotic. We'll talk about those towards the end. Okay, so let's talk about strong bases. So remember that strong acids, we just take negative log, right? But bases are different than acids, right? Acids always dissociate one hydrogen at a time, but bases don't go one at a time, right? Both hydroxides will leave at the same time. So when you do the pH of a base, again, the most common mistake made on exam 1 is this kind of a problem. Don't forget to remember to multiply by the hydroxides. Now, what do I mean multiply by the hydroxides? In this problem here, so we have a 0.0015 molar concentration of SrOH2, but there are 2 OHs. So we need to make sure we multiply that by 2, because when this dissociates, it makes an Sr and 2 OH minuses, right? So we need to remember to multiply. Again, this is the most commonly missed problem on exam 1. And exam 1's really hard. This problem is not hard, right? So I suggest we don't get this one wrong. So in this case, you can solve this however you like. I think it's easier to do it with the POHs. And I saw from our quiz, everybody was pretty good with those POHs. Or you can do with the KW. So whichever one you feel like doing. Okay, so here again is the part that people mistake. Do not forget this part. You need to multiply it by 2. Again, right here. If this was a 3, you'd multiply it by 3. If it was a 9, it's not going to be, but you would multiply it by that, right? So you need to remember that basis dissociate. Both the OHs come up at the same time. Now, I'm just going to do this with KW because I already have it written down. And again, we do this, we should have around 12-ish as our answer, and then just negative log of what we got. So this again, we had our quiz last week. We've been talking about this. We're good with this. It's just this piece. Don't forget if it's a strong base. Now, how do you know if it's a strong base? You have to memorize the strong bases, right? And everything else is weak. And again, I will go over these strong bases in a few minutes again, and I'm with our strong acids just to remind us which ones are strong and which ones are weak. Okay, so now let's look at our weak bases. Okay, so this again is going to be the Bronsted-Lowry definitions of a base or an acid. Remember, our bases gain, right? So here we have gained an H. Our acids lose. And this is going to be very important in a few minutes. So again, these weak bases only ionize a little bit, right? And so therefore we have a lot of our reactants left in the end. So finding the pH of a weak base is super similar to a weak acid, except one piece. So the process is exactly the same. But when we have a K and we're talking about an acid, it's a Ka. But if we have a K and we're talking about a base, it's a Kb. So if you have a base, a weak base, you have to use Kb. Just like when you had an acid, a weak acid, you used Ka. This is the second most common mistake people make. Now, what do I mean by Kb? Remember, Kb just means we're talking about a base, right? So we use it exactly like our Ka, like just like our Kc, just like our K everything. It's just specifically we're talking about a base. The bigger that Kp is, the stronger it is, right? It's just products over reactants. Same thing, right? Just remember, it needs to say Kb, and I'm going to teach you how to go back and forth to Ka and Kw in just a second. So if we look at these weak bases, our strongest weak base, right, would be the one with the biggest Kb. So these are all weak because all of these exponents are negative. So they're all weak, right? This is the weakest weak base, right? Because it's the smallest. So let's look at how we do find the pH of a weak base. Okay, so now we know that this is a base. Very important piece. If you have a base and you add it to water, you need to know what it's going to make, right? Don't just assume because I have this on your notes or it's like on the problem that you're like, oh, I don't need to do that. I'll figure it out later. No, it's going to get you later. When we put all this together in more difficult manners and on Wednesday, it's going to get you. You need to be able to write these equations. Okay, so if this is a base, bases gain, right? So NH4 bases gain, acids lose, right? This is our equation, right? So we need to make sure that we know how to write that equation because this equation is going to be what gives us our ice table, right? It tells us what we have in our ice table. So when we solve for our X here, when we solve for our X, we're solving for the hydroxide concentration, right? Before, when we were doing acid, that was our hydrogen concentration. This time, this is our hydroxide concentration. The process here is exactly the same as we did before, right? So we only have reactants, so it has to go forwards. I'm giving you a Kb, right? So if we have a Kb, that means I need to remember the number. I never remember 1.76 times 10 negative 5. I'm going to remember that number. So that means that this one's going to go down and these two are going to go up, right? Minus x plus x plus x. Just like we did before. And then 0.1 minus x, x, x. Now, when we write our product over reactant, again, it's just going to be, this should look just like we did last week. Right, x squared over, or x times x over this. Now we're going to assume that x is small, just like we did before. So see, so far, this is exactly the same as the weak acid ice table that we've done, except for this is hydroxide, right? And we need to remember that this needs to be a Kb. So if you have a base, there's two things you need to check. Is this hydroxide? Do you have your Kb? And I'll talk about when you don't have those in just a minute. Okay. Oh, someone asked a question. We do know K. I just need to put it on here again. There's K. We have it. And x is small should work because this is 10 to the negative 5 and this is 10 to the negative 1. So it should be fine. Now, for your quiz that you're going to take this week and your lecture checkup quiz, I want you to actually do the math for x is small, right? On your exam, I will let you reason, oh, the difference is -6. I don't need to do my x is small, right? But right now I need you to do the math with x is small. And not, if you're like, what? I'll go through it again. Okay, so if we assume our x is small, ignore x, that makes our life so much faster, right? And so when we do that, here's our Kb. It needs to be, it must have a B there. and then just x squared over 0.1. And so when we do that, multiply by 0.1, should make that an x, and then take the square root. And we do that, we get 1.33 times 10 to the negative 3. Now, this again is hydroxide, right? It is hydroxide. So now to check if our X is small, we want to see if the change in our reactant, our ammonia, was less than 5%. So we're going to take our X and divide it by the original concentration, or divide our original concentration by that, and see if it is indeed less than 5%. Now, this is 10 to the negative 1. This is 10 to the negative 5. That's a difference of 4. We're good. It's going to work. But right now, I need, on your quiz today and on your quiz on Saturday, I need to see this math right now. And then, right, I need to see you say that this is less than 5 right now, right? Until I am satisfied that you understand that concept, you need to check this. Now, again, this is the same thing if I asked you the percent ionization of this, you would be like, oh, it's 1.33%. Remember, this is like 2 birds, 1 stone kind of a problem. I didn't ask the percent ionization, but if I did, it's the same thing as X is small. Okay, so now we know, now we know that we're good, right? And so this, remember, this is our hydroxide concentration, not our hydrogen. So what people will do a lot of time, and they'll just be like, oh, it's just the negative log of this. Well, that's not your pH. That's your POH, but not your pH, right? So you need to remember that this is hydroxide. So again, you can do this with pH or POH. So if you did it with POH, you just take the negative log of 1.33 times 10 to the negative 3, and then whatever your answer is, you just take 14 minus your answer. And that'll give you your pH. Or you can do it the long way, which that's what I did here. You can do it the long way. And if you do it the long way, use your KW, just like we did before. And when we have our KW, we get our H2O plus, then we can take the negative log of it. So whichever way you feel more comfortable with doing this, it's fine with me. Okay, so let me go back a little bit and just talk about what I just did here. Okay, I'm just gonna go back here because I want you to be able to fill in whatever you missed what I just did. So when you have a weak base pH problem, the first thing you need to make sure you know how to do is write your equation. The reason this is so important is because you need to know what your X is. So when we finish and solve for X, we need to remember that that's hydroxide. Now we know it's going to go forwards. So it's going to be minus X plus X plus X, right? Then we're going to assume X is small, get rid of X. But then we got to check. So we assume it's small, then solve for our X. Here we are solving for X, remembering that this is not H, it is OH. OH. Okay, now that we have our OH, we need to check and see if the change is less than 5%. And again, I know this is going to work, and at this point, you pretty much should know that this is going to work. The reason is because the difference between the KB and the initial concentration needs to be, you're pretty safe if the difference is a magnitude of 3. So if the exponents are a difference of 3, you're good. These are a difference of 4. So we're definitely good. Sometimes you're okay with 2, but like that's a border. 3, pretty safe. 4, definitely safe. So we check that X is small. Indeed, we knew it was going to work, right? We already knew it was going to work because of the differences between this exponent, and this being a -1. Now we can find our pH. So when we find our pH, you can either use pOH or use kW. I do not care what you do as long as I see you do one or the other. What I don't want to do is I don't want to see this and then your answer. I want to see this work, or I want to see this work. I don't care which way you choose, but one of them needs to occur. Okay, any questions on this one before we move on? We're good? All right, let's try another one. Okay, so find the pH of a 0.0015 molar morphine solution. Morphine has nitrogen in it, so this is a base. I'm just going to tell you. You also kind of know it's a base because it's giving you KB. Those are our hints. Okay, so I don't know what the formula for morphine is, right? Who knows what the formula for morphine is? But it's a base, and I'm going to put my base in my water, and I know that base is gain. I don't know, HB plus. I don't know how to write that one. And I know that acids lose, right? However, this is so important. Do not skip this step, right? Do not skip the reaction step, because now when we do our ice table, right, you're going to have your base here, your H plus B. I'll write this neater in a second, and your OH, right? And so we have 0.0015 of our base. We don't have any of this. It can only go one way because we only have reactants. So this has to go down. The other one has to go up. Oh, someone had a question. The multiple hydroxide questions, that's only going to occur with strong bases. The rest of them, you'll see all the weak bases don't have multiple hydroxides. Hence part of the reasons why they're strong and weak. So you won't have to worry about that. Okay. Now, this has to go down. This has to go up, and this has to go up. What's going to go up or down by, right? X, X, X. Okay? So I'm going to write this all neater because I have it nice on here. This is the same thing. I'm just going to write it neater for you. Okay. So again, now, base plus water makes, I used HB plus, H plus B. I don't care how you write that. It just has to have an extra hydrogen on it. So that means it's going to be products over, I'll probably drive you crazy if I do that. So your KB is going to be the concentration of, oh, here we did it, BH plus, sure. BH plus times OH minus over our base, right? And so when we write that together, here's where we're going to say, shoop, X is small. Now, is X going to be small? Well, I don't know. I don't remember the K. Did I already show the KB? I did. 10 to the negative 6 is the KB, right? So why am I looking for that? So this is 10 to the negative 3, 10 to the negative 6. We should be okay, right? Definitely still have to check it, but at 3, you're pretty much always good. But sometimes not. So I always check 3s, always check 3s. Definitely check 2s. If the difference is 1, I guarantee you X is not small. But at 3, you should be good. Okay, so now we are just going to assume X is small. faster, easier math. Here is our KB. Right, just multiply 1.5 times 10 to the negative 3. 1.5 times 10 to the negative 3. It's supposed to be 3. And then just take the square root. Okay. So easier, lovelier math. And we get, oh, I have this nicer already for you. We get 4.9 times 10 to the negative 5. Now remember, this is our hydroxide concentration, not our acid concentration. So we can't just simply take the negative log of this and be done with it. That's not going to work. We need to check if X is small next. Next step. Is this change, did this decrease by less than 5%? I say it will, but it might be kind of close. So we take our X and we divide it by this original concentration. Someone's asking a question here. Oh yeah. There's a mistake in this one. Very nice. Nice catch. This should be a 3 right here. I'm not sure how I made that a 1 at some point. So see, I had a 1 here. That should be a 3. Unfortunately, I can't fix those, so I just need to remember that next time. Because they took equation editor out of PowerPoint. So now I can't change any of these numbers that I have. Okay, but everything, this is correct. This is completely correct. All right, so we get our X. And then we check, is X small? Yes, right? So we take our initial goes on the bottom, the X goes on the top. So it's X. And again, I always tell people, if they're like, oh, I don't know what to divide it by. You know what? Divide it by the only number that's in the X in your ICE table, right? Top left box. It's always your top left box. And indeed, it is less than 5. Check. X is small works. Okay, so now, remember, this is not hydrogen, right? So this one I'm going to do, so if we did POH, we could take POH is negative log of 4.9 times 10 to the negative 5th, right? And that gives us, oh, thanks, somebody put that in 4.31. And we just take 14 minus 4.31. I don't know what that is. And that will give you your pH. I think I have this up here. 14 minus 4.31. 9.69. Okay, so when you're doing this problem, and if you get a number smaller than 7, something's gone wrong. If you get a number bigger than 14, something's gone wrong, right? You kind of know your number has to be in between 7 and 14 because this is a base and this is pH. Those are the only options, right? So you know that if it's anywhere out of between 7 and 14, something has gone wrong. So I think, let me see. Oh yeah, here's my math, much nicer than it was before. And again, whichever way you feel more comfortable with doing, with either the KWs or the POHs, it's fine with me as long as you show your work. So on your lecture quiz today, I'll have like one of the questions will be like, find the pH of a weak base. And another question will be, find the pH of a weak acid, right? So it's just exactly what we just did, but showing it work. And we're going to do a couple more of these, but we're going to take a break from our ICE tables just for a little bit. And we're going to do something that's actually really fun. And this actually applies a lot to what we're doing in lab. It's figuring out the qualitative estimations of the pH of salts. So any ionic compound, right, that dissolves in water, that's a salt, right? And so we can actually figure out if something's acidic or basic based on knowing its conjugates, right? Here comes that conjugate acid base all over again and again and again. So if you have the conjugate base of a weak acid, your salt is going to be basic. Okay, so what I'm going to be doing now is I'm going to be breaking down the salt. I'm going to be breaking down into, do you remember when I said last week when I was like, it's really important that you can figure out the conjugate acids and conjugate bases just by looking at something, right? So like, for example, when you see Na, you should be like, where does Na come from? Oh, Na comes from NaOH. That's a strong base. When you see, if this was a base, if this was NaOH, this is a conjugate base of, this comes from H2CO3, right? So you should be, as we continue to do these problems more and more often, you should kind of be able to see if they're conjugate acids or bases, right? Now, why is that important? So if it comes from a strong acid or strong base, it's pH neutral, which we'll talk about. So we're going to always ignore these strong acids or strong bases. So that means that this is a conjugate base of a weak acid. This is going to be, if you put this into water, this would be basic. And you're going to be seeing this a lot when you're doing your lab, right? So it'll talk about the pHs, and you're going to be using this skill to figure it out. So now let's look at this one. So we break it up. So we break this up into NH4 and to Cl. Well, Cl comes from HCl, right? So we can just ignore it because this is a conjugate base or acid. If it comes from a strong acid or a strong base, it is pH neutral, so we ignore it. So if we see something that comes from a strong acid or a strong base, we're like, meh, it's not going to affect our pH at all. NH4, now a lot of times people are like, how do I know if it's NH5 or NH4? Here's my question. If it seems foreign to you, it's probably wrong. NH5, have you ever seen NH5? No. NH3, that's ammonia. We know that one. It's more likely to be, so I always say you kind of have to go with your chemistry gut on these. And the fact that this has to be a conjugate acid here, because if this isn't, right, if this is an acid, a cation, and this is an anion, it has to be an acid, right? And so therefore this is going to be acidic because it's the conjugate acid of a weak base. The conjugate acids of a weak base are acidic. Okay. So again, conjugate acids of weak bases are acidic. Okay? Okay. Let's try some more of these. So we're thinking everything as conjugates. So the stronger the acid is, or the stronger the base is, the weaker the conjugate is. So let's just talk about acids for a second. So the stronger the acid is, the weaker the conjugate base. So for example, if you had HCl, that's a super strong acid. That means that its conjugate base is very weak. So for example, so an anion that's a conjugate of a strong base is going to be pH neutral because it's so weak. If it comes from, again, the anion that comes from the conjugate base of a weak acid is basic. So if we look at our F minus comes from HF. This is a weak acid. Weak acid. This means that this is a weak base. Okay, so you're going to get used to doing this. It just takes a little bit of thinking when you're doing this. So let's just look at these. I'm just going to give you two ions. Okay, so I have a table here, but we're going to try and not use the table. So NO3 minus. When you see NO3 minus, what common acid or base or chemical formula have you seen that's dealing with acids and bases does it bring to your mind? Yeah, Nitric acid. That's exactly what it should bring to your mind. Nitric acid. Okay, this comes from nitric acid. That means that this is the conjugate base of a strong acid. This is the conjugate base of a strong acid. So therefore, it's going to be neutral. Because remember, if it comes from a strong acid or if it comes from a strong base, it's pH neutral. Okay, now this. Well, there's only really one option of where this came from, right? This must have come from HNO2, right? That's the only option here. So HNO2, this is a weak acid. That's supposed to be okay. It's okay. If this is a weak acid, this is its conjugate base. This must be basic, weakly basic. This is a conjugate base of a weak acid, so therefore this is basic. Okay, so I'm introducing this now. We're going to do this more because I feel like the first time you see this, it hurts your brain, but we're going to practice this a bunch later too. And then you're going to see it actually is kind of fun, especially when you're in the lab and you're like, oh, I know this is acidic because here's what's in here. And then you're like, oh my gosh, I can't believe I remember that. But we're going to practice these more later. Let's go back to this Ka and Kb of our acids and our bases. So remember, if you're doing the pH of a weak acid, you need to have a Ka, and your X is your H plus ion concentration. If you're doing the pH of a weak base, you need to have a Kb, and your X is the hydroxide concentration. And if you're like, it's okay, we're gonna practice this more. So Kas are by far more prevalent in the world than Kbs. Even if they're talking about a base, they still publish the Ka. Well, if you have a base, you can't use Ka, you have to use Kb. So we need a way to get to Kb from Ka and vice versa. Because remember, if we have an acid, we have to be using Ka. If we have a base, we have to be using Kb. So what if you have a base, but they give you Ka? How do you get Kb? Well, we can use our little ideas of our little KWs. So remember this from like kinetics, right? We're going to actually do this more when we add equations. We did this a little bit in equilibrium, right? And kinetics, remember this kinetics, we did this, and then we did this at the beginning of chapter 14, right? If you add it, if you add equations, then you multiply the Ks. So here's me adding a weak acid and a weak base dissociation. I get water makes H3O plus OH. Well, that's the same thing as H times OH, right? So therefore, Ka times Kb equals Kw. So you can use this, right? So, and let's look at how we use this right now. Okay, so this is my favorite molecule. It's called nacho. Get it? Nacho. So find the pH of a 0.1 molar of nacho solution. The question is this an acid or a base? Okay, so now when you see this, remember that Na comes from NaOH. It is not going to affect our pH in any way, shape, or form. So we completely ignore it. So what we're really finding the pH of is we're really finding the pH of this. So that is CHO2 minus, right? Because if this was a +1, then this is a -1. So if I put this in water, is it an acid or is it a base? See, this is where the fun comes in, right? So this is going to be a base, which makes this an acid. So when the base is gained, so this is going to be H plus OH, not minus. So this is our new reaction. And again, this is important because this is what's going to give us our ice table, right? These are the numbers that we're going to be using in our ice table. I have this nicer right here. Hold on a second. There it is, all nicer for you. Okay, so for this problem, we've decided that this is a base, right? Base, acid, conjugate base. If this is a base, our X, right, when we finish, this is going to be our hydroxide concentration. But they gave us a Ka. We cannot do the problem with a Ka. We're going to need to change this Ka into a Kb, right? If you're finding the pH of a weak base, you need to make sure that you remember that this is OH and you need Kb. So we're going to need to convert this to Kb. That's supposed to say Kb. Okay, so first, let's just set up our ice table. Simple, this ice table, now we've done this a few hundred times, right? Minus X plus X plus X, because if we're only starting with reactants, it can only go one way. It's got to go towards our products. So it's going to be 0.1 minus X. X, X, right? Now, remember, Ka times Kb equals Kw. Right? So therefore, Kb equals Kw over Ka. Kw never changes. It's 1 times 10 to the negative 14th. They gave us Ka, which they had to have. This gives us our Kb, which is 5.6 times 10 to the negative 11th. Right? That's the Kb. So again, weak base. This X, when we solve this, it's OH. We had to change our Ka into a Kb. So now we have, so if we write our expression, Kb equals OH minus over our base, right? And so when we do that, we have 5.6 times 10 to the negative 11th equals X squared over 0.1. So someone asked the question, what if the cation was the conjugate acid of a weak base? Then it would be a weak acid problem, right? That's part of the fun of the rest of this chapter and all of next chapter. You're just going to be given salts. You're just going to be given ionic compounds. And you're going to be like, I'm going to be like, find the pH of this salt. And you're going to be like, and I'll give you only Kas. Right? So you have to be able to look at a salt. And again, that's how we're going to practice this more. You have to be able to look at an ionic compound and know if that ionic compound is going to be an acid or a base, right? Then we're going to start our ice table. Now, when we do this, well, I'll use a little X here, times 0.1 times 1 square root, and we get our X. Okay. So questions so far with what we've done here? Any questions so far? Okay. I'm going to keep going. So this is what I just did. I assumed X was small. Now, is my X is small going to work? Oh yeah, for sure. Definitely going to work. I have no doubts on that. Negative 11 and negative 1 is definitely going to work. Okay, so we solve this and we get X is 2.4 times 10 to the negative 6. So remember, on your quiz that you're doing today and the one that you're doing this week, I actually want to see this X is small. I actually want to see you do it. on your exam, I will be okay with you just saying the difference is a magnitude of 10. It definitely works. But right now, we need to do it. And again, we knew this x was going to be tiny because of the difference, right? Negative 11 and negative 1, it was definitely going to work. So again, what do you put in the x is small? You put your x and that original concentration. That's what goes in this x is small. It needs to be less than 5 for our math to be nice and tidy. So our x is small worked, check, we're good there. Then we just need to find our pH. Now remembering that this is the concentration of OH, right? So if this is the concentration of our OH, that means we have to take, POH is easier, negative log of it, subtract from 14. Or we can use KW, whichever one. So if we do POH, remember POH is just negative log of OH. And then whatever your answer is, you take 14 minus your answer. Which everybody got that right on their, almost everybody got that right on their quiz. So I have no doubts. Now remember, we decided at the very beginning, right, that this was a base. Therefore, if you somehow forget to put these up here, or you write an H plus right here, there's all sorts of things I've seen happen. We decided this was a base. If this is a base, that is the pH of an acid. That is not right, right? 14 minus this. This is the pH of a base. Right? If we decide this is a base, then our pH must be greater than 7. So when you're finding the pH of a base, you got to have a KB, right? Got to have a KB. Have to remember that this is OH. Your answer must be greater than 7. If you're finding the pH of a weak acid, in that case, that's going to be your H+. It's an easier problem, right? Your pH should be less than 7. And everyone gives you KAs, so you're always going to have your KA. Okay, so now let's try a fun one. Not that these weren't fun. Okay, what's NaA? I don't know, right? Okay, so if a 0.5 molar NaA solution has a pOH of 5.5, what is the Ka of HA? Whoa, okay, so, oops, the first thing we need to do, what is NaA? Okay, well, Na comes from NaOH, so I don't care about Na. It does not matter to me. A minus, what happens when I put A minus in water? Well, it definitely can't lose, right? There are no hydrogens, it must gain. So that must mean that this is a base. That is an acid. Acids lose, bases gain. Okay, this is a basic solution. Okay, this is a base. Got it. Okay, so that means when we do our ice table, we're going to have A minus, HA, and OH. So the first thing we had to figure out was, is this an acid or a base? When you're given a salt, which means an ionic compound, number one, you need to know if it's an acid or a base, right? And again, we're going to practice that more. So we decided this is a base. So therefore, this is OH here. Okay, so what else do they give us? pOH. pOH is 5.45. Okay. So what can we get from our pOH? Well, remember when we did this with acids, right? If we wanted the concentration of H+, you could just take 10 to the negative pH. Well, then if we have the OH, we just take 10 to the negative pOH. right? So if we just take 10 to the negative this, then we'll be good. So someone had a question, what if it was a weak acid and a weak base? Yeah, that's really hard. We're not gonna talk about those for a while. We'll actually talk about it in a little bit, but that math is very difficult. Okay, so we can find our OH concentration by just taking 10 to the negative POH. So if we take 10 to the negative POH, here's our OH concentration. That's our X. They gave us X, right? That is, right? Because remember, X, that is our OH concentration. They're giving us, so they're telling us the change. So this is 3.55 times 10 to the negative 6, right? Which means this is, if this is, so I'm gonna, right, so this goes down by negative X, right? But they're giving us our X. Right, and so this goes down by minus X. So the change here is going to be minus 3.55 times 10 to the negative 6. So this is going to be 0.15 minus 3.55 times 10 to the negative 6, which you know what that ends up being? 0.15. Because the change is so small. It does change, remember, but it changes at 0.00000, way beyond where our significant figures are going, right? And so now we can figure this out. Now, when we do this, remember, these are all talking about our basic reaction. So when we put these into an equilibrium expression, this is going to give us our KB because this is a base. The question is asking for Ka, right? So when we solve this, all we need to do is plug these into our equilibrium expression, right? We need to remember this is Kb though, not Ka. So when we do this, right? These are our X's over our change, which it doesn't really change, but this isn't our answer because this is Kb. And remember, Ka times Kb equals Kw. So we need to use our Kw to get to our Kb. Our Ka. Okay. So to do that, trying to think here. I'm going to write this over here. Kw never changes over and that becomes something I do not remember. I have it on the next page though. Okay, so all this math is here also. We get 1.2 times 10 to the negative 4th as our Ka. Okay. So what we just did here was I gave you a salt. We did two problems where I gave you a salt and you had to figure out the pH of the salt. Sorry, you did figure out the pH, but the first thing we did was you had to figure out if it is an acid or if it is a base, right? Using the principles I just taught you. And we're going to do more of those right now. After we decided if it's an acid or a base, then we wrote the equation, right? Otherwise, we don't know what goes up here if we don't write the equation. We have no idea what goes up on what the identity of these things are. Then they gave us our change. So it was actually easier than our other problems. But when we finished, we had a Kb, but we had to convert that into Ka, right? Because the second you decide this is a base, you need to memorize this OH and Kbs. That's what you're dealing with. If it's an acid, these are H pluses and they are Kas. Okay, so let's do more salts and then we're gonna do more of these problems. Okay, so now some cations can be thought of as the conjugate acid of a weak base. The stronger the base is, just like we talked about, the weaker the conjugate acid is, right? So if your cation comes from a strong base, like sodium hydroxide, it's going to be pH neutral. If your cation comes from, if it's the conjugate acid of a weak, comes from a weak base, then it will be acidic. Okay, so for like NH4, where does NH4 come from? NH4 comes from NH3. NH3 is a base. Therefore, its conjugate is acidic. This must be a weak acid. So again, we're going to keep putting this in again and again and again. Okay, one other fun thing, and we're going to talk more about this one throughout the semester, is highly charged metal cations are acidic. Now, what do I mean by highly charged? Like +3 would be considered highly charged. This you're going to use so many times in your lab, so many times. Small, highly charged metals are going to be acidic. And this is when we'll talk about loose acids and bases in just a minute. But just remember, small, highly charged, acidic, right? This is going to become very handy in your lab, very handy. Okay, so let's practice with a few of these. Okay, so now. Okay, where does this come from? So first of all, if you remember, I said if you see nitrogens, that's a sign that this was a base, right? So nitrogens are signs of a base. And so the question is, and this one's a little hard, where did this one come from, right? Which base did this one come from? So this came from likely NH3, which means that was our base. Sorry, just reading a question here. Okay, so the conjugate acid of this weak base, so this is going to be acidic. Remember, so if it's a conjugate acid, acids lose, so therefore it's going to be acidic. Now, how about this one? Calcium 2+ comes from calcium hydroxide, which is a strong base. If calcium hydroxide is a strong base, that means that calcium is pH neutral. Chromium 3+. So the question is this going to be acidic or neutral? This would be considered a highly charged metal cation. So therefore, this is going to be acidic. Okay, so now, this slide I think is very important. Strong acids and strong bases. These strong acids and strong bases. So we need to remember these strong acids and strong bases. So again, memorize these. Everything else is weak. We're pretty good with the acids. Perchloric is the only one that might get us, but otherwise we're good. We're pretty good with these acids because we've used these enough now. The bases, if you look at a periodic table, which unfortunately, whenever I hold up my periodic table, it disappears. So I'm gonna just hold it right next to my face. If you look at your periodic table, Li, Na, and K are like all in a line on group 1. And then if you just move over 1, Ca, Sr, and Ba are like the next, I call it like a Jenga block. So the strong bases kind of look like a Jenga block on your periodic table. So that's kind of how you can remember those. So it goes like Li, Na, K, then you go over and it goes Ca, Sr, Ba. So it's like, look, it looks like a Jenga block. on your periodic table with group 1 and group 2. So I think that's the easiest way to memorize the strong bases. Those are a little more difficult for us because we don't really deal with bases as much. But as long as you remember, it's kind of like a Jenga block. That should help you with your strong bases. Okay, so we're going to practice a few of these. Okay, classify these as acidic, basic, or neutral. Okay, so now we look at this. Na, NaOH, Cl, HCl, strong acid, strong base. This is going to be neutral. pH 7. Ca, calcium hydroxide, strong base. NO3, nitric acid, strong acid. pH of 7, neutral. KBr, KOH, strong base. HBr, strong acid, pH 7. See, this is why you need to know these, right? Because these are going to become very important. They make your life much easier here. Okay, now let's look at the next one. If the salt, the ionic compound, is the counterion of a strong base, then it's going of a strong base, and the anion is the conjugate of a weak base of a weak acid, then it will form a basic solution. Okay, what does that mean? Na, NaOH, don't care. Ca, CaOH, doesn't matter. K, KOH, doesn't matter. All those come from strong bases. So I cross them off because they are not going to contribute to the pH. They're pH neutral. So now we need to look at this. F, that comes from HF, right? If HF is a weak acid, its conjugate is a weak base. So this is going to be basic. This comes from acetic acid. If this is an acid, its conjugate will be a base. HNO2. This is a weak acid, which means this must be a weak base. So when you're doing these, I think it helps to try and figure out where they come from. Because if you can figure out where it came from, then you can identify it as a weak acid or a weak base. Now remember, even if I just say acid or base, I mean weak, unless I specifically say the word strong. Okay, now let's try another one. So if you have a cation that's a conjugate acid of a weak base, and the anion is the conjugate base of a strong acid, it will form an acidic solution. So what does that mean? When I see this one, I see Cl, HCl, doesn't matter, not going to come from, it's not going to matter. NH4, NH4 is NH3, right? That's the conjugate. This, I can't make it 3. This right here is a base, which makes this a weak acid. So this solution is going to have a pH less than 7. The last one, and this is the one, again, you're going to use a lot in lab. If it's a highly charged metal cation, it's going to be acidic. This, again, this comes from HNO3. Doesn't matter. pH neutral. Not going to use it. Okay, let's do last one. Now, this is the question someone proposed. We're going to do an example with this one because this one's difficult. What happens if the cation is the conjugate acid of a weak base, right? And you've got a weak acid and a weak base. So like, okay, so NH4 comes from NH3. So this must be acidic. F comes from HF. So this must be basic. Oh, they do not cancel each other out. Okay, well, in that case, we actually have to look at the Kas and the Kbs, right? And this is actually going to be an acidic solution because HF is a stronger acid. Its Ka of HF is bigger than the Kb, so therefore it's acidic. Now this one is really difficult. I'm going to show you an example with numbers. right? This is the hardest when we do these, but I'm going to show you with an example with numbers. We'll make it easier in a second. Okay, so we're going to practice a few of these. Okay. Are these lining up? Yes. So HNO3 is conjugate base. It's a strong acid. So therefore, its conjugate base doesn't matter. How about HNO2? So the conjugate base of HNO2 is the conjugate base of HNO2, nitrous acid, is NO2 minus. This is a weak acid. So therefore, this is going to be a weak base. Now let's do our strong acids in a second. Remember, if it comes from a strong acid, pH neutral. If it comes from a weak acid, if it comes from a weak acid, it is a weak base. Weak acids have weak conjugate bases. Let's do another one. NH3, its conjugate is NH4 plus. NH3 is a weak base. Because we memorized it, it's not strong. If it's a weak base, that means its conjugate acid is a weak acid. NaOH. Its conjugate acid is Na. It's strong. It's pH neutral. So strong bases have pH neutral conjugate acids. Weak bases have weak conjugate acids. Weak acids have weak conjugate bases. Okay, are you ready to practice? Okay. Is this an acidic, basic, or neutral? What do you think? What do you think? I'm going to wait for your answers on this one. Acidic, basic, or neutral? Okay, so like if I asked you to find the pH of this one right here, you'd have to decide, is this an acid or a base? So the first thing you do is you break it up. So I'm seeing lots of answers coming through. We're in like a 50-50 shot on it. We've decided it's definitely not neutral. That's the one we've decided it's not. So we break up the ions. Okay. Then we think, where do they come from? So Li comes from LiOH. LiOH, that's in our Jenga block. That is a strong base. So therefore, it's pH neutral, right? PO4, that comes from H3PO4. That is a weak acid. So therefore, PO4 3- phosphate must be a weak base. Therefore, this solution is going to be a basic solution. So if we had to find the pH of this solution, when we put this in water, that would be our equation, right? So that means if we did an ice table here, that means that our X would be hydroxide concentration, and we would need to have a KB to do this problem, right? Okay, let's try again. All right, NH4Cl, acid, basic, or neutral? I'm seeing much more of a consensus on this one. Okay, so we break them up. So NH4 plus comes from NH3. NH3 is a weak base. So therefore, NH4 plus must be a weak acid, right? Cl minus comes from HCl, which is a strong acid. Strong acids don't contribute to our pH at all. Therefore, this must be acidic. So when we put this in water, if this is an acid, acids lose. Bases gain. When we did an ice table, our X would be H3O plus, and we would need to use a Ka. Okay, let's do some more. KNO3, again, my question, acidic, basic, neutral. What do we think, acidic, basic, or neutral? I'm waiting for a couple more here. I'm seeing a lot. Okay, so we break them down. Break them into the ions. We're like, K, where does K come from? Oh, K comes from KOH. That is a strong base. pH neutral, doesn't matter. NO3, where does NO3 come from? NO3 comes from nitric acid. That is a strong acid. So if this question, if someone said, find the pH of this one, your answer would be like 7. My answer is 7. There is no math needed. It's just 7. Okay, so hopefully that's giving you a little bit more ideas on these. So we're just gonna do a couple more, and we're gonna do them a little faster now. Okay, NaCl, what do you think? Acidic, basic, neutral? Oh yeah, I'm seeing these ones. We're like, oh, we're getting this. Lots of these now, yes. Na, NaOH, ignore it. Cl, HCl, ignore it. pH, 7. Okay, how about this one? K2CO3, acidic, basic, neutral. See, when you start getting the hang of it, it's actually kind of fun. All right, I've got 3. I'm waiting for some more. Got a few more. K, come from KOH. Ignore it. CO3, right? That's from HCO3, which is a weak acid. So CO3 must be a weak base. This is going to be greater than 7, basic. All right, acidic, basic, neutral. So this one, right, HNO3, ignore it. NH4 comes from NH3. NH3 is a base, so NH4 must be a weak acid. We said ignore NO3, this must be acidic. Okay, here's a fun one. What do we think about this one? Okay, so NH4 comes from NH3. We decided that's a weak acid. CO3, right, comes from HCO3. So we decided this is a weak base. So the question is, I don't know. Okay, so let's break it down. This is the one that I said was really fun. Okay, so break down our ions. Now we need to look at which one has a bigger Ka or a Kb. So let's look at the Ka for NH4 is 6 times 10 to the negative 10. Super weak, okay? The Kb for CO3 is super weak, but negative 10 is bigger than negative 11, so NH4 wins, and this will have a pH of less than 7. This will be acidic. Probably like 6.89, but it will be acidic. Barely acidic, but it will be acidic. All right, so if you've got a weak acid and a weak base, the only way to tell if the pH is going to be acidic or basic is if you compare whoever has the bigger Ka or Kb. Now remember, because this is an acid, you've got to use its Ka. Because this is a base, you've got to use its Kb. Okay, so just need to make sure you're using the correct one. Okay, so those are kind of fun. We're going to be doing a lot of those in your homework. Okay, now what about if you have a polyprotic acid, like phosphoric acid or sulfuric acid or carbonic acid? They have more than one H's, so that means they have more than one Ka. But in general, if the Ks are really different, you can kind of ignore all of them, right? So for all of our polyprotic acids, you can ignore the contributions to the Ks. Just remember when we just did the mixtures of acids and we only kept the one that was the strongest? It's the same thing with polyprotics. So let me show you this. So here is, let's not do sulfuric, let's do phosphoric. So look, here's it's strong, first of all, right? It's strong. And then it's 10 to the negative 3, negative 8, negative 13, right? Those aren't going to really have that much of an effect on it. Or look at this one, look at absorbic, negative 5, negative 12, right? The difference here, when you actually use these, are the dissociation is so small. Remember, if it's a negative exponent, that means it's going to be reactant favored. So these are lying so far towards the reactants that their dissociation is going to be negligible. It's not saying that they're not going to dissociate. They're just going to dissociate to such a point that we can't even measure it, right? The only one that's not negligible is this one. 10 to the negative 2. Yeah, it's just not it kind of has an effect. And that's the only one we'll do. So when it comes to H2SO4, we're going to talk about, we can use the H2SO4 as the H3O plus for our second ionization. So I'm going to show you how that works. So the only one you really have to worry about is H2SO4. Okay, so for example, here's carbonic acid. Look at the differences, right? This isn't going to matter. It's just too small. So when we do this, this ends up just being a straight ice table with a weak acid. So when we do this, we do have two equations, but this one's going to be negligible, right? Just because that's our second Ka, and it was so much smaller, it's not going to make any difference in our answer. So when we do our ice table, we do the same thing as we've done before, minus x plus x plus x, 0.12 minus x, and then it ends up being x squared, and then we're going to assume x is small. And our first Ka was 10 to the negative 7. Was 4.3 times 10 to the negative 7. Negative 7, negative 1, we're good. X is small is going to work. Right, so we just have x squared. Also, once you've done a lot of ice tables, you try to stop using them and you just figure out how to set up the math. You can't do that this week. Okay, I need to see your ice tables in your work. I need to see the physical ice tables this week in your work. So don't be skipping the ice tables, even if you're like, oh, I figured out how to do the math without the ice tables. You're doing the ice tables this week. I need to see to make sure that you understand how to set these up. Okay, so we assume our x is small. Sure, that's going to work. And we get x is 2.2 times 10 to the negative 4. We should just check it, even though I'm sure it's going to work. But when we do it, we know that negative 7 is definitely work. And again, we're just ignoring this one because its contribution is going to be so small. Okay. So we get 2.27 times 10 to the negative 4 is our x. We're going to divide it with 0.12 to check and see if x is indeed small, which it is. We knew it would work because of the difference. Our x is H3O plus because this is an acid, right? Hence we use Kas, acid, Kas. Our x is H3O plus. So to get our pH, we just take negative log of our acid, right? And then these are our concentrations, right? And so this was our reaction that we used. I just have the generic ones up here. And that is our pH. Oops. Okay, so now, one last problem. What about H2SO4? It's the only one I said that you can't ignore the second ionization because it does make a difference. It's actually not that much harder of an ice table. It makes your math a little bit harder, but when you do the first ionization, this is what you've got, right? And so, what I'm going to say, I just want to see here what I used. So I used 0.01. So when you do your first ionization, this is going to be 0.01 molar, which makes this 0.01 molar, and this 0.01 molar, right? So that means this is how much you're starting with of this. So when you do this in an ice table, this is 0.01 molar, right? So, and this is stays the same. So you're actually going to use, you're going to do two ice tables in one, right? Because the first ionization is complete, you can use this in the second one because this, remember, 100% ionizes. So it goes, you can start using your second equation. So what does that mean for our math? What does that mean for our ice table? So remember, I use 0.01 molar. So that means that I had 0.01 molar of this and 0.01 molar of that to start, right? I don't know the concentration of this. I do know the concentration of this. I have the initial concentration of this H3O plus, it's 0.01. I have the initial concentration of this, it is 0.01. I do not know this equilibrium, and I do not know that equilibrium, right? I'm assuming my H is small, my X is small is going to work. So we're going to say it's going to go forwards. But here's where it becomes trickier. Because you've got a minus X, just like we did before, but because you have a value here, you actually can't do X is small. It just doesn't work. I'll just warn you, it doesn't work. So you have to do the math. You have to do the quadratic formula. And again, this is only going to occur with sulfuric acid. This is the only thing that's going to matter is with sulfuric acid. So I'm going to show you this math. You got to make it into a quadratic formula. And again, right, negative b minus b squared minus 4ac over 2a or something like that. And again, you're going to take the positive value, can't have a negative value. So this is our x. So again, can't use your x as small on this one. Two reasons, it doesn't work. And our Ka was 0.01 and our concentration was about the same. So it doesn't work, right? Those are too similar. It's not going to work. Okay, so we have x is 0.0045. So then we have to plug it in to all our values. Plug all of it in, right? And again, we want the pH, so all we need is 0.01 plus x. So here we are, 0.0145, negative log of that. And we get 1.839. So you can see it actually does change the pH, right? Because if we just took the negative log of 0.01, so if you did, sorry. If you just did the negative log of 0.01, you would get 2. Obviously it's 2, yeah. So you can see that that second ionization does have an effect on its pH. So you can't ignore it, right? If you want to try, you could do the same thing with the other ones that have their KAs are greatly different, but you'll see there's no difference in the two answers. They're exactly the same, right? It's just H2SO4. So watch out for the H2SO4. You can't ignore it. How do you do it differently? This is it. It goes in both of these, right? Because those are your starting concentration, or those are your initial starting concentrations. And then you just solve for the equilibrium points. And you have to do that. You have to do the quadratic formula. That's the only thing. Okay, so any questions on where we ended today? So this is all we have for today. We're gonna do strengths of acids tomorrow. The questions. Successive approximations doesn't really work for this one. It's because the minus x and plus x, because x is in both places. Hence why it doesn't really work, because you can't approximate both x's at the same time. But you could try it. You could definitely try it. You would put it in for this one. There's where you would put it in. But the quadratic is probably a bit faster on this one. Okay,